Hi, I'm Anastasis, and today I'm going to be talking to you about Runway, specifically about some of the backend challenges that we faced in our machine learning-based video editing tools. I'm super excited to be speaking to the Scale conference and looking forward to any questions you have at the end of the presentation. So I'm going to be speaking primarily on the technical challenges that we're facing, delivering video and processing video on the fly, but I'm going to start by giving some context on what Runway is and what challenges that we're solving. So the way we like to describe Runway is like having your video production studio right inside your browser. So essentially, we're building a professional video editing suite that lives on the browser and utilizes cloud-based machine learning tools to be able to make those techniques a lot more accessible and not require to have expensive hardware or resources to be able to edit video. We do that by leveraging state-of-the-art machine learning for tasks like segmentation or in-painting or a variety of other tasks, and by trying to also simplify the complexity of traditional video editing tools as much as possible so that you can very easily use functionality that's traditionally been has a steep learning curve and traditionally been very complex to use without spending a lot of time and without needing to do a lot more tedious manual work, and instead of focusing more on the creative parts of the video editing process. This is kind of how video editing feels like today. There is a lot of interface complexity. It's very error prone, and it requires expensive hardware and resources to be able to use. And we try to simplify that process as much as possible. We try to not compromise on flexibility, so still being able to create very compelling, complex video projects, but take away some of the accidental complexity that's involved in traditional video editing workflows. So we try to build tools that are very simple on the interface level and try to abstract away a lot of the complexity that is required in order to use those techniques. Runway is used by a variety of teams and audiences, from very power VFX users who are specifically interested in the advanced VFX tools that we provide, such as rotoscoping or motion tracking, to more casual video editors who want to use Runway as their main editing tool, kind of end-to-end build video projects inside Runway. Specifically, teams as well that want to work with video and have a quick turnaround time. So they want to be able to iterate fast, to try a lot of ideas, and do so without having to necessarily deal with all the complexity that's involved traditionally in sharing video projects, in kind of collaborating, and having to run expensive rendering that might take a long time. Our main focus at Runway is building very intuitive ML-based tools. We focus a lot on making machine learning techniques very practical to use and figure out what are the best interfaces that we can build to be able to utilize those tools. We focus on machine learning, not because for the sake of focusing on machine learning, but because we've seen that with a lot of those video processing techniques, it's really the best tool for the job. So when it comes to things like segmentation, with rotoscoping, or in-painting or tracking, we've seen that the machine learning-based techniques deliver results at much better latency and much better accuracy than more traditional computer vision techniques. And so we're focusing a lot on taking state-of-the-art machine learning that delivers these high-quality results and figuring out what's the easiest way to deploy those and make those accessible for users without necessarily needing to have any technical know-how for how those techniques work or extensive machine learning knowledge to be able to use those techniques. We offer a variety of tools that leverage machine learning, and the list is only growing every month, but I'll mention a few of them. So as I mentioned, we have Green Screen, which is a rotoscoping tool and one of the most popular tools in the platform, but we also offer tools for in-painting, which is erasing objects in a video, or motion tracking, which is following specific points of interest in a video. We have a series of audio-based functionalities, such as clean audio, which removes background noise in your video, which is especially useful for interviews. We have beat snapping, which is a very fun feature specifically for editing music videos that allows you to take a music track, identify all the beats in the track, and then offer them as snapping points inside your editing flow. So you can edit videos that utilize the beats of the music in a lot faster, a lot quicker. Finally, we have super slow motion, which is a tool we actually just released, which allows you to take a low frame rate video and then increase the frame rate by up to 10x. So if you bring 30 frame FPS video into Runway, we can turn it into 300 FPS video. And that allows you to create very compelling slow motion animation into your footage that might not necessarily be shot at that high frame rate. One of the main goals of our team and what makes working at Runway so fun is the ability to turn research into production with a much streamlined, accelerated timeline than most companies do. And this is something we focus a lot on and always iterate on how can we make this process faster. So we know that with the pace that AI research is advancing, we need to become very good at porting new models, new research that's coming out, developing in-house by a research team as well, and bring that research into production in a way that results in very usable tools and very smooth interactive tools. So research at Runway works very closely with the rest of the product organization to be able to deliver those models to production. Now I'm going to speak a bit about our technical approach, specifically how we structure our services to be able to deliver outputs from those models in an interactive, streamlined way to our client. That's the browser-based video editor tools. So one big important part about our approach is that every model is turned into an HLS stream. So we use HLS as the common interface that clients interact with to be able to stream results from our models. So we use HLS not just for the original video content, but also for any processed version of the content via our machine learning algorithms. So we use HLS for, say, the optical flow. So optical flow is very important for tools like motion tracking to be able to identify what motion is happening in the scene. We use that for our green screen tool to generate segmentation masks for specific subjects in a video. We use it for depth estimation to be able to create effects that leverage depth to create depth of field effects and other compelling effects to our video editor. The pipeline in general looks, as I mentioned, is very unified across our different machine learning models that we support in Runway. So we have our source video, and then we create a playlist, HLS playlist, for specific versions of the video that are processed by different machine learning models. So in some cases, like the depth estimation case, we can start generating the depth information from a video as soon as the user upload finishes, because it doesn't take into account any other inputs. In some other cases, like segmentation or tracking, we use human guidance to specify exactly what we want to focus on. So in the case of green screen, we want to select the subject that we want to mask. In the case of tracking, we want to select points of interest in the video to track. And in those cases, we can pre-generate that content ahead of time. We need to take the human guidance into account. So we focus a lot on making those models very fast so they can be used interactively by users. So as they're editing video, they can start streaming results for the model as soon as possible. This is how our pipeline looks in a very simplified form. So when the user makes a request for a specific segment of the output stream, first of all, we need to fetch the relevant content, which might be the user's video or a subset of the user's video that's relevant for that specific segment. And then we process that through one of our machine learning models. And we focus a lot on optimizing those models to be able to run at interactive frame rates. In some cases, we might make some compromises in terms of using a smaller backbone or quantizing the model, and in order to make sure that the latency is within tolerable levels. And finally, we encode the result back into either a video, in some cases like the segmentation or depth, or in some other cases into JSON blobs that define for example, with tracking where the point of interest have moved throughout the rest of the video. This is a subset of the challenges that we face that are particularly relevant, I believe, for this audience. So first of all, a big challenge around latency. We want to make sure that we can run inference with our machine learning models and do any transcoding required on the fly, in some cases with computationally expensive models. So we don't want to compromise on the quality of the results, but we also don't want to have the model's inference take so long that the user will wait a long time for it. So this is always a balance that we try to find between accuracy and latency. Second of all, we want to generate temporally stable outputs. So we want to make sure that there is no flickering involved in the model outputs. But we want to do that with a stateless protocol like HLS. We want to be able for the user to go to the end of the video and then be able to stream results from the model interactively without having to process the video from the beginning up to that point. And so we make some specific design choices to be able to allow that. Finally, it's really important for us to bring the human in the loop. So provide ways for the user to give guidance to the model outputs. We know that models make mistakes, and so we want to make sure that the user can make any refinements necessary and correct mistakes that are made by the model to be able to get the output at the quality that they require, which for creatives, that's the requirements for quality can be quite high. And so we want to be able to support that. In order to make those challenges a bit more concrete, I'm going to focus on one example. As I mentioned, this is one of our most popular tools. It's called Green Screen, and it's our rotoscoping tool that allows you to create a mask around a specific subject in the video and track that mask throughout the rest of the video in a temporally consistent manner. This is a quick demo of how the tool works. So the user makes a selection at the initial frame of the video with a few clicks that generate an initial mask, and then they propagate those results to the rest of the video automatically. If they detect any mistakes made in other frames of the video, they can make additional keyframes by adding more clicks at those specific frames. So ideally, we try to make the techniques work well enough that you need to create keyframes at as little amount of frames as possible. The strategy that we follow for our green screen tool is the following. We basically divide the task in two parts. The first part is generating the keyframe masks with human guidance, so with the clicks that I mentioned earlier. So this is a model that just operates on a single frame of the video and takes both that frame and a series of clicks into account to generate an initial mask that's used as a keyframe. Once the user has made keyframes in the video, then we propagate those masks to every other frame of the video in a temporally consistent manner. And this is the task of the propagation network. First of all, for the clicks to mask network, this is a model that's responsible for generating the original keyframe masks that are then used for propagation. So what the user can do with this model is basically provide include and exclude clicks to specify the areas that the user wants to incorporate in the mask and areas that they don't want to incorporate a mask. So if the model makes an initial selection that includes something that the user doesn't want to be part of the mask, they can add an exclude click to remove that part. This is a different task. So this task is called interactive segmentation, and it's different from the more common semantic segmentation. Semantic segmentation is being able to detect a fixed set of categories in the input video, in the input frame. In our case, we want to support a variety of different objects that the user can segment, or a variety of different combinations of objects. So for example, the user might want to segment a person and a microphone, and we want to make sure that the user can make that selection. And so the clicks to mask network should be able to select objects or combinations of objects that are unseen during training. One of the big challenges here is being able to simulate how the user will perform those clicking sessions to specify what they want to select in the input frame. So the way we do that is by using a synthetic data generation approach where we simulate how potential masking sessions might work like. So masking session is basically, it consists of a few rounds of clicking where the user adds includes and exclude clicks on a frame, they get back the result, and then they add more clicks to further refine the result. And we want to be able to simulate a variety of clicking behavior because we have users that are that might add a lot of clicks to make sure that the mask is perfect, and users that might expect that they would get good result with 1 or 2 clicks as well. So we're simulating we build a probabilistic model that simulates a variety of scenarios here to make sure that those will match what we will see in production. And we make a few other assumptions about the clicking behavior. For example, if the user has clicked on a specific region of the frame, the next click is probably not going to be that close to the original region. So we incorporate those assumptions into our probabilistic model that we use. The propagation network is the second step of the process. So once the user has created some high quality keyframe masks on a very small sample of the frames of the video, we now want to propagate them to every other frame of the video and propagate them in a way that's temporally consistent. So the propagation network is responsible for using information from those keyframe masks and then propagating that information to generating masks for every other frame. Obviously, the latency and performance requirements of this model are a lot stricter because this is a model we want to perform inference on for every single frame of the video and not just individual frames where we can wait a bit longer to run inference on. The architecture is very similar to the other network, but we have an additional space-time attention mechanism that basically allows us to look at different areas of the keyframe mask to figure out what's relevant to incorporate in the current frame. And then we also have an edge refinement module that allows us to perform a better matting, which is basically predicting alpha transparency at the edges of the subject. Rotoscoping is traditionally used to do compositing, which is bring a subject to a different background. And in order for that blending to work correctly, we want to avoid having hard edges. And so we want to predict a mask that's kind of continuous in values rather than a binary mask that's where an area is either fully included or not included. An important part of our keyframe-based propagation is the ability to support random access. As I mentioned, we want to be able to process different parts of the video with a segmentation model independently. And so we can't incorporate any sequential mechanism, which is very common in video processing techniques. So we can't incorporate the outputs of the model to predict other outputs of the model, because that will require us to create a dependency where we need to process things in order. And in our case, we want to support the use case where a user might go to the end of the video and want to see how the mask is generated there without having to process the entire rest of the video to get there. And so we always only consider keyframe masks, but we never consider other outputs of the model. And this makes it a lot easier to perform this random access. So it creates a much better user experience because the user can navigate to any part of the video and have that working very fast. But it also allows us to perform some additional optimizations, such as doing more prefetching. So if the user is at a specific time in the timeline, we want to be able to prefetch a lot of segments ahead of time. And we want to parallelize that effort so that there is not only one worker that's responsible for processing those segments, but rather we can send those tasks to multiple workers and process a larger amount of the video ahead of time to ensure that when the user presses play, we have an interactive output. Finally, I wanted to mention some challenges ahead that we're facing. We're always looking to, as I mentioned, simplify the experience of editing video so that users can focus on the more creative aspects of that flow. And so right now we're working on providing a text-based interface to our video editing functionality, being able to perform any of the tools that I mentioned earlier, but via a text interface and via natural language input. So this introduces a wide variety of other challenges that I hope to cover at a future talk. But if you're interested in more of the challenges that we're working on, I'm more than happy to talk about them. I want to thank you for your time, and I'm looking forward to hearing any questions you have.